For centuries, scientists saw light as something smooth, continuous, and wave-like. It rippled, bent, and interfered just like water. The wave theory of light seemed perfect. But in the late 1800s, a strange experiment began to break that certainty. It was simple, stubborn, and completely unwilling to behave the way physics said it should. That experiment was the photoelectric effect, and it would lead a young Albert Einstein to one of the most revolutionary ideas in science. Light is made of particles. The story begins in 1887 with Heinrich Hertz. While studying electromagnetic waves, he noticed something unexpected. When he shined ultraviolet light on a metal surface, tiny sparks appeared. Electrons were being ejected from the metal. This became known as the photoelectric effect, but the effect didn't follow the rules. According to classical physics, brighter light should give electrons more energy. More intensity meant stronger waves, and stronger waves should shake electrons loose. But that's not what happened. Experiments revealed three deeply puzzling behaviors. First, low-frequency light, no matter how bright, never ejected electrons. You could blast the metal with intense red light for hours, and nothing would happen. Second, high-frequency light ejected electrons instantly, even if the light was extremely dim. There was no buildup, no delay. Third, the speed of the ejected electrons depended only on the light's frequency, not its brightness. This made no sense if light was just a wave. Classical wave theory predicted that electrons should slowly absorb energy, shine bright enough light for long enough, and eventually, electrons should pop out. But physics had hit a wall. In 1905, Albert Einstein proposed a radical solution. He suggested that light wasn't just a wave. Instead, it came in tiny packets of energy. Today, we call them photons. Each photon carried a specific amount of energy. If the photon's energy was too low, it couldn't eject an electron, no matter how many photons you threw at the metal. But if the photon's energy was high enough, it could knock an electron out instantly. Einstein's idea explained everything. The metal required a minimum amount of energy to free an electron. This minimum was called the work function. If a photon's energy was below that threshold, the electron stayed put. If it was above, the electron was released immediately. Brightness only increased the number of photons, not their energy. So bright red light still had weak photons. Dim blue light had powerful ones. Einstein even created an equation describing the photoelectric effect. The energy of a photon was equal to its frequency multiplied by a constant. This matched every experimental result perfectly. But Einstein's idea was so bold that many physicists didn't believe it. One of them was Robert Millikan. Millikan spent 10 years trying to disprove Einstein's theory. Instead, his experiments confirmed it with extraordinary precision. Millikan showed that the kinetic energy of photoelectrons increased linearly with frequency, exactly as Einstein predicted. The evidence was undeniable. Einstein's explanation didn't just solve a scientific puzzle, it forced scientists to accept that light had a dual nature. This was the birth of quantum mechanics, a field that would reshape our understanding of atoms, energy, and the universe itself. The photoelectric effect also became the foundation for technologies we use every day. Solar panels convert photons into electricity. Digital cameras rely on photoelectric sensors. Night vision devices detect photons in low light. Einstein's insight didn't just win him the Nobel Prize, it built the modern world. So the next time you take a photo or unlock your phone with facial recognition, remember, it all works because Einstein challenged the wave theory. The photoelectric effect wasn't just an experiment. It was the moment physics stepped into the quantum age. If you enjoyed this breakdown, make sure you like, subscribe, and share Talking Tech, where complex science becomes clear.